Welcome everybody. You're watching Mr. Fugu Data Science. This is the third installment for our 10 data science interview questions. Let's get into this. You have a disease that occurs in 1% of the population who test positive. You have a 3% false positive rate, 4% false negative rate. Now, if you have a test come back positive from some random person in the general population, what's the chance they actually have the disease? And you have these four choices right here. And you got to think about this. You only have a minute to answer any of these 10 questions. So you have two really high and two pretty low answers. And you got to figure out, well, what is this asking me? You have to understand that this is a Bayes problem, all right? So let's look into this a little bit. So if you notice here, we have the probability of A given B. So you're saying the probability of B given A times the probability of A over B, where B equals this. And you'll see that this means not A. So you have to figure out, how do I break this down? So setting this up so it makes a little more sense for us, we have to say that the probability of having this disease, given that I tested positive, would be this equal to the probability of the disease occurring times the probability of the testing positive, given that you have the disease, over probability of the disease times the probability of testing positive, given that you have the disease, etc. Right? So you have to say that if you're testing positive, given that you have the disease, we have to use 1 minus the false negative value, where the false negative is our 4%. So the probability of no disease is 1 minus the probability of the disease, where we're saying that 1% of the population has this disease. Now, the testing positive and not having the disease is a false positive, where that was 3% of the population. We plug these in and you end up getting 24%. So eyeballing this, you would have an idea that the higher values in the first two answers were dubious, considering that you had a 1% chance of actually having the disease. So then it was saying that you would have a really high chance of testing positive and actually having it. Now, second question. In general, what is the introduction of a regularization term doing to the cost function? How does it affect it? Your answers are looking like 3 of them are fairly reasonable. The first one I would reject is it doesn't affect the cost function. That's just a ringer. You could just drop that. The next 3 you have to evaluate and really think about what's going on with the regularization term in general. You're taking let's zoom out a little bit there so you can read everything. So what you're doing in the introduction of a regularization term, let's back up. We need to evaluate the basics. In general, you're trying to minimize overfitting and generalize your model. That's something that is paramount. We're not really looking to make a one use case scenario particular to that data set. You're trying to create a model that generalizes to our unseen data and make a model that'll work for that. You're also trying to decrease the amount of variance and minimally increase your bias. If you know what the regularization term is, it's a penalty term that you add, allowing you to tune that model. And think of adding more complexity to the model, the more you need to penalize it. Interestingly enough, when you look at this Gaussian noise and you say, well, it adds a term to account for that Gaussian noise. Well, that's really interesting, because in a neural network, you can add noise to your data to simulate a regularization term and a small training set to avoid overfitting. That's a real use case, but that's not what's going on with what we're being asked and what you need. Think of that regularization term as something like an L2 norm. Refresh on if you're considering lasso or ridge regression, for instance. If you're looking at a convex function, this seems like a very plausible answer as well, except the case is that you're not always dealing with convex functions, okay? If you're going back to the term of like an L2 or L1 norm, then you could have that case. So it's only working in some situations for regression. My ultimate answer would be to say that we're using this in regards to penalizing larger parameter values. What's the difference between a k-nearest neighbor and a k-means? Well, the k-means, we're dealing with a clustering algorithm, whereas the k-nearest neighbor is mostly used for classification. There are circumstances of regression. You could think of using this for similarity, like you're measuring some distance and you're checking or evaluating to see how far this this point is from some given stationary point that you're evaluating. And you could think of this as a supervised algorithm that we're placing the input and seeing how it reacts, okay? And you can input values of k and see how this affects your error. So as you're decreasing your values of k, the closer you get to 1, you'll notice that you'll have an issue with stability of your predictions. And one of the good things about this, it doesn't have any underlying assumptions. The larger your data set, you start having issues with performance. It just slows down incredibly. K-means is interesting because you're partitioning your observations into your clusters, and you have to basically like do guesswork on how many clusters you would like. You can do something called like a scree plot or like an elbow plot and get an idea of how many clusters that you should use with your data that you could run separately. But you're trying to basically minimize the amount of cluster variance between your groups, all right? Then we are trying to figure out what's the difference between type 1 and type 2 error. And you have to remember, and you say, oh no, I got an idea, but I might get this one confused, and it happens, you know, because they're such generic terms. So you have to just remember that the first one, you're just rejecting a true null hypothesis, and then the reverse for the other where you're actually keeping a false null hypothesis. So the first one, you're keeping something that you should reject, all right? So if you can remember that. And then if you're asked about precision and recall, what are they and how are they related to the ROC curve, you might have to do some thinking. But the precision is a percentage of your true positives. Your recall is a percent of your correct positive predictions, and then it relates the ROC curve through the relationship of basically the recall and specificity, you know, like a true negative, like the percent of those. And if you're putting those all three together, you're dealing with like a classification model basically. So if you had to explain like a L1 versus L2 regularization, just remember that L1 is your lasso and L2 is your ridge. And how are they different? You can remember that the lasso is doing like a feature selection and you're penalizing your higher coefficients. And you can remember that it shrinks less important features towards 0. Whereas the ridge is like a bias variance trade-off. And if we look here, if you really want to get nitpicky and just make it really for brevity, the ridge has this squared term here, whereas the lasso has the absolute value. So we can look here at this and notice the slight distinctions between these. I got rid of the rest of the function because really what we're evaluating is this, okay? You're asked, are there any limitations or disadvantages when you're looking at a linear model? And you gotta do a little bit of thinking. A linear model has issues with overfitting and outliers. So if you have some data where you just have some like really large numbers, like a couple of them, throwing off everything, for instance, if you had a line that, you know, everything was really close together with like, you know, a range of maybe 10, and all of a sudden you had something that was like blown out of proportion, it was like 200, and that outlier is going to skew everything. And you have some issues with overfitting. So overfitting can occur if you have some random noise that you end up modeling and assume that this is an actual relationship in your data. That's problematic. And also, if your data is not linear, then you have a, you know, terrible model. You can pay attention to my little emoji, but there are cases when you have the ability to do transformations and make your data look, so if you thought your data was linear and then you find out, oh, it's not linear, you could try some other transformations like a log or a square root or something like that to see if maybe that helps you get closer to where you're at. One other issue is assuming that your attributes are independent. And then you say, uh-oh, what if there's autocorrelation that occurs? And so now that throws everything off and messes up your model when you had the assumption that it was a linear model and it was not. And you can't account for that. And let's say you have this really fun, nasty boss, as we usually do, usually incompetent. Your boss gives you this data set to evaluate, and then you do some investigation and you find that you have some correlation between a few of your variables, and your boss wants you to perform PCA. Doesn't say anything else to you. And then you have to say, well, should I use the PCA and not touch these variables, or do I deal with the correlated variables and then move on to doing the PCA? And this is something that happened to me personally. And what you'll notice is that, interestingly enough, and it's a little elusive, if I do not take care of these correlated variables, it will actually create dubious effects. So I end up exaggerating the variance that's explained and really a problem. So if you had a low amount of variables that you're dealing with, but quite a few of them are correlated, this is going to really throw off all your results. So you need to really pay attention to that when you're investigating your data. All right. Now let's talk about multicollinearity and what are some considerations you should think about when dealing with this. So we should back up and think about this occurs when you have some kind of independent variable in your regression model that has a relationship, and you end up getting a problem when you're estimating the relationship of your independent variable to the dependent variable. And what we need to consider is that if we start getting rid of things, you have to worry about losing your information. So you can't just discard things, arbitrarily. Your interpretation of your coefficients now is difficult, and you can't exactly trust your p-values because they're going to be off and also affect your precision. Now, what can we do to try to work with this and make it better? You can actually use something called the VIF, which is a variance inflation factor, and you can run this through some software and you'll get an actual number. And depending on what this number is, like if it's really low, like a 1, you won't have any correlation, but it's like something 1 to 5. The higher you go, the more correlation you have, and if it's greater than 5, it's completely correlated. Another way you can think about dealing with this is featuring lasso or ridge regression and penalizing your terms. The last question, give me a few ways how you would select an important or useful variable. You can do this a few ways, but other than what I mentioned. But I decided to put lasso and then do some feature selection like forward or back propagation. You can also try to remove your correlated variables. Now, I did have one extra bonus question, but it's not completed yet, and I can show you that before we sign off. So we have this question that's asking about singular value decomposition, SVD. And this problem I'm not done with, and it's very involved, but you have 4 choices. And are you converting this to a Jordan form? Are you inverting a singular matrix? Is it related to low rank? Are you solving for overdetermined system of linear equations? And which of these are an example of SVD? That's what it's asking. It's not one clear answer. That's the problem. So when you're looking at singular value decomposition, you have to kind of start breaking this apart to figure out what each portion is asking me and what's really going on in the initial portion of SVD. So I'm going to continue this in another video, probably, I don't know yet. But the Jordan form is interesting because it is related to the SVD, mainly in terms of the diagonalization of your matrix. Inverting the singular matrix, I haven't thought about that too much. The low rank approximation, that is a type of example used for singular value decomposition, as well as solving overdetermined system of linear equations. And the problem with this is almost all of these are all relevant examples. Since that's the case, I have to expand on this answer. So that's why it's not finished. But that is something that came up for a job interview that I had, and I couldn't exactly answer this. So I would like to say thank you for watching. Like and share this video, and if you subscribe, turn on that notification bell. I hope this brought utility to someone. Thank you for watching. I'll see you in the next video. Bye.